Welcome! In this video, I'll show you how to solve problem 2.6 as it appears in the 4th edition of Griffith's Introduction to Electrodynamics. This problem states the following. It says, find the electric field at distance z above the center of a flat circular disk of radius r, which is what I'm showing you right here, that carries a uniform surface charge sigma. What does the formula give in the limit where r goes to infinity? Also check the case when z is much greater than r. Alright, so this situation is very similar to the one that we did in problem 2.5, which is also in my channel. I will link it in the description because it will be very useful to understand this one. But basically, it's the same problem, but this time it's not a line charge. This time we have a surface. So for that reason, the electric field will be calculated a little bit different, right? So the electric field for a charge distribution, we know is 1 over 4 pi epsilon 0. And then we have to integrate. Now, it used to be lambda, right? We were doing one-dimensional integration, but now it's sigma, right? So it's a surface distribution of our r vector. And we also have to go through, of course, we have to divide by the magnitude of r squared. And now we still need our, in this case, it's going to be some dA, right? It's going to be our surface segment here. Okay, so what else? Now, of course, be very careful. I use the r hat notation. You may want to use the r vector, right? And instead of r hat, you can write it as r vector divided by the modulus. So it would be a little bit different, but it's the same in the end. Now, the point is that we need to find this r vector. So, of course, first we need to set up a coordinate system. In this case, once again, just like we did in the previous problem, we will use cylindrical coordinates. So cylindrical, and we will center it right here. So that's going to be our 0. So we will have rho, theta, and z. I'm going to use rho instead of r because we already have r here and there and there. So, you know, we just want to be careful. Okay, so the point is, these are going to be our coordinates, and thus this here is going to be a distance z in the z direction. And let's say that we are interested in some point over there. This is going to be, oh, actually just randomly, right? And now this is a surface, not only a point, so maybe we are interested in this part dA right there. So we want to find this distance, right? We want to find whatever amount this is. So this is our vector. So how do we find this? How do we find this vector? Just as always, we begin at whatever point we choose, and then we need to find a way to walk from here to there, right? That is the definition of a vector. A vector tells you where you start and where you end. So if we begin at some random point, so if we begin at some point, you know, r in the r direction, then how do we go here? Well, regardless of where we are, whether it is here or there or there or there or there, it doesn't matter. Wherever we are, first we need to walk a negative r here being the coordinate, right, in polar coordinates of where we are, we need to walk a negative r in the rho direction, right? Basically, we need to go towards the center. However far away we are, which is what the r coordinate tells us, we need to go towards the center, right? Perhaps we could be careful and use a different letter instead of r to not make this confusing. Perhaps we could just go ahead and say rho, for example, just so that we don't get ourselves confused with all the different r's that are already out there. I think it may be a good idea. So instead of saying r, I'm going to say rho. Of course, the meaning is the same, but it's simply to avoid confusion. And then we need to go up z in the z hat direction. Now, this is different from the problem 2.5, where we had simply this circle, this line segment that was in the shape of a circle, because then we didn't have this amount as a variable. It was a constant. Now it is a variable. Okay, so what is the modulus here? Well, the modulus is going to be, so the unit vector is going to be this divided by the modulus. So we have minus rho in the rho hat direction, plus z in the z hat direction, and we divide this by the square root of rho squared plus z squared. Okay, so now we plug all of this in, and let's begin finding the electric field. So the electric field is 1 over 4 pi epsilon 0. We integrate sigma, now r hat, which is, as we saw, minus rho in the rho hat direction, plus z in the z hat direction, all of this divided by this r vector squared, but what is, well, actually cubed now because we introduced another one when we took this. And what is that vector? That vector is simply the square root of r squared plus z squared cubed. So we get this to the 3/2. And then we have this dA. So let's now take apart this dA. We are now integrating this entire disk. So dA, this is going to be our variable rho, right, which is this polar coordinate, is going to be rho d theta. All right, so we are integrating in polar coordinates. We also integrated in polar coordinates last time, except that rho wasn't variable, so that's why rho didn't come into effect. Okay, so instead of having dA, now we have rho d theta. And what are the limits of the integral, right? We have two integrals. So d rho goes from 0 to big R, and theta goes from 0 to 2 pi, right? We are integrating over the entire disk. Now, you could, if you have watched the previous video, you already know that this integral will be 0. If you don't know that because you didn't watch it or maybe you have forgotten, don't worry, I will explain it. Okay, just a little bit heads up, this will be 0. And because of the symmetry, it makes sense, right? Every contribution from here will be cancelled out by the symmetric part here. And every contribution here will be cancelled out by one here, the one from here by here, the one from here by there, right? There's always going to be a point that is opposite that will cancel out the radial direction. It will only will have in the z direction. But I will show you mathematically where that comes. Okay, so first step, we now want to take apart everything that we have here. Okay, so let's see. We can, of course, take out this sigma. So sigma doesn't depend on any of our variables, so we can just take it out. And then let's separate our integrals that go in the theta direction and what goes in the radial direction. So in theta, what do we have in theta? Well, there is no explicit dependence, but always be careful. This rho vector, this vector that goes from the center to whichever point we are at, maybe there or maybe there, right? This would be our rho hat direction, depending on where we are. That changes, right? If we are in a different angle, theta, our vector is different, right? That angle is different from this angle, if this is theta, for example. So it changes depending on the angle. So it is not constant. And in fact, the rho vector, right? I went into more detail in the previous video. I'll just do it quickly here. This is rho cosine theta in the x hat direction plus rho sine theta in the y hat direction. And thus the unit vector is simply dividing by its modulus, which gives us cosine theta in the x hat direction plus rho sine theta in the y hat direction. Oh, sorry, not rho. The rho goes away. There we go. So that is the unit vector. So you can see it has a dependence on theta. Okay, so let's now begin separating the integrals. So first, let's just separate the sum, and then we'll separate each one of the integrals. So we have 0 to 2 pi, 0 to r of minus, and then we have rho cosine of theta in the x hat direction plus sine of theta in the y hat direction divided by rho squared plus c squared, z squared 3/2 in rho d theta. So that is this first part. Then we have plus z in the z hat direction. We can take it out of the integral because it doesn't depend on rho or theta. 0 to r. And then we simply have here rho d theta divided by rho squared plus z squared to the 3/2. Okay, so these are the two integrals that we need to solve. We already know that this part should give us 0, but let's corroborate. Let's make sure that this part does indeed give 0. So let's see. This is sigma 4 pi epsilon 0. And here we have minus. Now let's separate the radial part, so the d rho, from the d theta, right? Thankfully, they are not intertwined. It's not like you have the cosine of theta times rho or something, like put together or something, so you can just separate it. So we have minus the integral from 0 to 2 pi of cosine theta in the x hat direction plus sine theta in the y hat direction d theta. And then we have integral from 0 to r of rho squared d rho divided by rho squared plus z squared to the 3/2. Now this integral looks a little bit nasty, so perhaps you would want to begin with this one. Now let's take a look at this integral. This is integral of cosine plus integral of sine. The integral of cosine gives us sine theta between 0 and 2 pi, but this is 0 minus 0 when we evaluate the limits. And the integral of sine will give us minus cosine of theta between 0 and 2 pi, which gives us minus 1 when we evaluate at 2 pi, minus 1 when we evaluate at 0, which is also 0. So this integral is 0, which means that the product of this integral, 0 times the other integral, it doesn't matter what this integral is, it's still going to be 0. Okay, so that's why this is 0. We already knew that that was going to be the case, but that's just a quick corroboration. Okay, so we need to now solve this integral. So we have z hat. Now notice that there is nothing regarding theta, right? There's only d theta. So that integral is trivial. It's simply 2 pi, right? You get theta evaluated between 0 and 2 pi, which is 2 pi minus 0, right? So simply 2 pi. 2 pi. And then we have integral between 0 and r of rho d rho, rho squared plus zeta squared 3/2. We have seen how to solve this one in the past. What we do here, right, let's say this is integral I, let's just call it I. So to solve it, what we do is we use a substitution. So 0 to rho d rho, integral from, over rho squared z squared 3/2. Now, how can you know what to do here? Well, notice that we have our variable here plus a constant and the derivative of the variable up there. So if we use a substitution that is like u is rho squared plus z squared, then taking du will give us 2 rho d rho, because this does not depend on rho, so when you take the derivative, it's going to be 0. So rho d rho is simply du divided by 2, right? This comes from there. So if we plug this into our integral, let's see, our limits of integration, maybe let's change them. I usually just behave lazily, but let's see. U is rho squared plus z squared. So if rho is 0, we get z squared. So this is between z squared and big R squared plus z squared. Okay, so those are the limits. And now instead of rho d rho, we have 1/2 du divided by u to the 3/2. Now this integral, that's the same as simply u to the minus 3/2. And that way it's a lot easier to integrate. So minus 3/2, the du is a little bit too far up, du. And now this integral should be relatively simple. So that integral gives us minus 2u to the minus 1/2, right? Because if you take the derivative, you get minus 1/2, which cancels this out, and you end up with u to the minus 3/2. And you evaluate this between z squared and r squared plus z squared. Okay, now those twos cancel out, and we end up with minus, and now we evaluate. So we get 1 over the square root of r squared plus z squared minus 1 over the square root of z squared, which is simply z. But since there's a minus sign outside, we change the signs inside. And there we go. So that is the integral. So now let's plug it back into our formula for the electric field, and we will have our results. So the electric field is going to be 1 over 4 pi epsilon 0. And then we have, let's see, sigma times 2 pi. Let's see, we have a z that was already outside. We have z hat. And then we need to multiply by 1 over z minus 1 over the square root of r squared plus z squared. All right, so this is the result for the electric field. Now, let's just quickly corroborate this. So we have, to continue now, they ask, what does the formula give in the limit where r is very, very, very large? So if r, right, if r is very large, if it tends to infinity, then we have this formula except for the fact, okay, so let me write it down. So 1 over 4 pi epsilon 0, 2 pi sigma z z hat. And then what do we have here? 1 over z minus, and now r is so much larger than z that this z makes no difference. So this is basically 1 over the square root of r squared. All right? So the square root of r squared is simply r, so there's no need to worry about the absolute value. And here we have 1 divided by r, which is ginormous. It's 1 divided by 5 trillion or something, which is this part is basically 0, right? It is, you are 1 over a number so large, you basically get 0. So this is what we end up with. Of course, 1 over z cancels out the z that is already there. And this right here is our result. Now, of course, we can simplify it just a little bit more. So this, we can simplify the pi, the 2, and we end up with sigma divided by 2 epsilon 0 in the z hat direction, which right now doesn't ring a bell probably, but this is exactly the formula that we get when we find the electric field of an infinite plane, which is very interesting. If we have an entire plane, not just a circle, if this circle extends further and further and further and further, it basically is an infinite plane, right? The xy plane in its entirety. And that is exactly the field that we will calculate later on when we want to find that directly. So it's very nice that we actually found it. Now, what about the other limit, right? In the limit where z is much, much, much greater than r, when we are very far away. Well, when we are very far away, let's see, so the electric field, 1 over 4 pi epsilon 0, 2 pi sigma z z hat, 1 over z. Now, if z is much, 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 much greater than this r part, then we get 1 over z. Now, for this term, we will have to approximate a little bit. So to just go ahead and approximate, what we will do is we will factor out z squared, right? So we'll factor out z squared, so we get z here, and we get, I'm going to do it like this, 1 plus r squared over z squared. Why do we do it like this? Because in this case, z squared is much larger, which means that this is 1 plus something very, very, very small. And why do we do it like that? Because here we want to use an approximation that is very, very common. If you have never seen this before, I do encourage that you pay attention. I have a few videos on this, but I'm still going to explain it here just in case. So if we have 1 over the square root, I'm going to write it like this, of 1 plus something very small, which in this case is r squared over z squared. This is to the 1/2. This is, of course, the same as 1 plus r squared divided by z squared to the minus 1/2. Right, so the binomial theorem, I do recommend that you check it out again if you haven't. So just as a quick reminder, what does the binomial theorem tell us? Well, we know from the binomial theorem that if we have 1 plus y to the nth power, this is simply the sum from, some k equal to 0 to infinity of n over k, y to the k power. Now, what does that mean? Well, that simply means, right, if we expand this, first we have the term where k is equal to 0. That means n over 0, y to the 0, which is, of course, simply 1, right? This n factorial over n minus 0 factorial, that's simply n factorial over n factorial, which is simply 1. And then we have y to the 0th power, which is 1. And then we have the next part, which is going to be n over 1, right? And then we have y to the first power. Now, in this case, we get n factorial divided by n minus 1 factorial. Now, that division, of course, gives us simply n. So this is simply n times y. Now, we could continue going, but the next term is already y squared, and y, it represents r squared over z squared. So y squared would be r to the 4th power over z to the 4th power. And we are already saying that r is much, 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 much smaller than z. So if r over z is already small and r squared over z is already very small, this is just so ridiculously small that we shouldn't even bother considering it. Okay, so plugging now in our actual results, right? I mean, using this for our actual case, we have this expansion is going to be 1 minus, right, n is minus 1/2, r squared divided by z squared. And now we can just plug this back in here. So maybe let's make some space. We know that this square root is equal to what I wrote down in red. So actually I'm gonna, go a little bit cleaner. Okay, so minus 1 over z. And now we multiply by 1 minus r squared divided by 2z squared. Okay, so multiplying through, we get minus 1 over z times 1, which gives us minus 1 over z. And then here we get plus, there we go, plus r squared divided by 2 z cubed. So z cubed. All right, so of course this part cancels out, which is why it's important that we go to second order. If you had only done this to first order, then you would have gotten that this is 0. Okay, so that's why we had to go to second order. Now, of course, this amount is not going to be very big, which is why you had to go to second order. Okay, and then we have 1 over 4 pi epsilon 0 times 2 pi sigma. Now, this z will cancel out with a part of that, so we get r squared divided by 2z squared in the z direction. The 2's cancel out. We end up with pi r squared times sigma, and that is precisely the area of our disk, right? The area of our disk is pi r squared, and the total charge is simply going to be its area times its charge per unit area, right? So what we have here, this entire thing is simply the total charge, right? This thing here is simply the total charge Q. And this equation is simply the electric field generated by a point charge. And that makes sense because the case when z is much, much greater than r is the point where we move very far away, right? When we move far away, that disk doesn't look like a disk anymore. It looks like a point charge, which is why the end result is approximately the electric field of a point charge. So there we go. I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.